This is America's most trusted chocolate bar, especially by kids. What does it have to do with machine learning? A lot. Well, guess what? If I eat this chocolate, a lot of sugar, right? The blood sugar in my bloodstream will increase, okay? And it's gonna range between 100 and 150. If I eat more of these, let's say 2 or 3 or 4, then the blood sugar will increase even more. So the more chocolate that I eat with sugar, the higher the bloodstream sugar will be in my system. Hey Zoe, do you want one? Chcesz jedno Reese's? Proszę. And now, if she eats this, her blood sugar will increase. The effect of Reese's on blood sugar can be described with linear regression, right? We have the amount of Reese's, could be measured in grams or whatever, right? Kilograms maybe. And the outcome would be your blood sugar. And it's a continuous variable, right? From 70 to 140. The amount of Reese's displayed on the x-axis will have a direct impact on the blood sugar level displayed on the y-axis. And here we have observations that had eaten a given amount of Reese's and the blood sugar level on the y-axis. Now drawing a straight line will show us the relationship between the amount of Reese's and the blood sugar level. Keep in mind that in linear regression, the y variable, the outcome variable, has to be continuous. In this case, the blood sugar level is a continuous variable. So let's say that we can fit this into linear regression. But what if I changed our causation? What if I said that the amount of Reese's will impact whether I am getting diabetes or not? What is the probability of getting diabetes after eating 10 Reese's? What is the probability of getting diabetes if I eat 40 Reese's? What is the probability of diabetes if I eat 100 Reese's today? We'll take a look at the number of Reese's eaten once again on the x-axis, and those will predict our diabetes test outcome. And the outcome can be either negative or positive, a binary outcome. So for the negatives, we have 5 observations that are scattered around the smaller amount of Reese's, and for the positive outcomes, our observations are scattered around the higher amount of Reese's. The occurrence or lack of diabetes can be described with a binary variable, 1, 0. 1 for diabetes after eating 200 Reese's, and 0 for lack of diabetes, right? If I don't eat sugar, right? Now, what we said before is what is the probability of diabetes? Probability of diabetes being probability of 1. 1 being our business success, and 0 being our business failure. But we always try to describe the probability of 1, probability of having diabetes. Let's take a look at the math behind our probability of business success. We will start with something called odds. Odds that you can see on the left-hand side of the equal sign can be expressed as P divided by 1 minus P. P stands for probability of business success, and 1 minus P stands for probability of business failure. Now our odds is equal to the EXP of something that you already know, the regression line, B0 plus B1 x1. We can also apply a log transformation to this equation and get a natural logarithm of odds equal to B0 plus B1x. After applying a few more mathematical transformations, we end up with the probability on the left-hand side of the equation sign, and on the right-hand side, we see our logistic regression. So keep in mind, the P, probability of business success, is what we are going to predict using our logistic regression. We just described 2 different situations. Linear regression, describing the amount of sugar from Reese's that could potentially affect the amount of blood sugar in my bloodstream. And the second situation was that we were trying to predict the probability of getting diabetes after eating an amount of chocolate. So the amount of chocolate can impact the bloodstream sugar, but also in the long run, the amount of Reese's can impact the occurrence of diabetes, 1 and 0. Amazing. Now that we know a few facts about logistic regression and what variables it uses to train and to test and our labels 1 and 0 binary, let's take a look at how to code that logistic regression in R and RStudio. So let's go to RStudio, and in our script, let's install a library that will load some data regarding diabetes. Okay, let's do it then. Install.packages, open parentheses, open double quotes, mlbench. mlbench is a package in R that has a lot of data sets that we can use to practice what we learned in this class. So now let's run this command return control enter. It's going to ask me if I want to restart R prior to installing. I'm going to click yes. This package was previously installed on my computer, so that's why I have to reinstall it. So I am reinstalling mlbench. It's going to the mirror, to the crayon, and it's showing the folder at which the package is located. Okay, so now the next step after installing the package would be to load it with the library statement. Library parentheses mlbench. Okay, command return control enter. I have loaded my library. So now I can use a data function with parentheses to call any data set that is available in the mlbench package. Okay, and I have a list of beautiful data sets. I highly encourage you guys to use these data sets and practice after this session. Okay. And each of these data sets will be shortly described in the yellow window that pops up when I hover over these data sets. But what I'm looking for this session is the Pima Indians diabetes data set. So let's click on this. Okay, good. So now if I run this using command return control enter, in my environment, right over here, what I'm going to get is my Pima Indians diabetes data set, 768 observations and 9 variables. If I click on this blue circle here, I'm going to get the list of my variables, and I have variables such as pregnant, that's numeric, glucose, that's numeric, pressure, that's numeric, triceps, that's numeric, insulin, numeric, mass, numeric, pedigree, numeric, age, numeric. And last but not least, diabetes, a factor of 2 levels, negative and positive. So this suggests that all these numerical variables are our features, okay, our independent variables based on which we'll predict if a person, if an observation has diabetes, okay, and if the test results is positive or negative, okay? I'm going to swoop this way to show you negative or positive levels, indices, and in my data I have 1, 2, 1, 2, 1, 2. Okay, so our next step would be to look at our variables and see if we have to massage anything, change anything. The first few variables, our features that we identified as potential features, are all numeric. That's wonderful. We have pregnant, glucose, pressure, triceps, insulin, mass, pedigree, age, all of them are numeric. I'm assuming they are good to go. But the last one, I'm going to scoop this way. Diabetes is a factor with 2 levels, negative and positive, 2, 1, 2, 1, 2, 1. In the earlier part of this video, we had discussed that our outcome variable has to be binary, 1, 0, 1, 0, 1 for business success, 0 for business failure. So we have to convert this 2, 1, 2, 1, 2, 1 to a binary 1, 0, 1, 0. In our case, negative is labeled as 1 and positive is labeled as 2. Now here's the trick. If I subtract 1 from this variable, what I will get is 1, 0, 1, 0, 1, 0, 1. Okay? And in our case, in the new case, number 1 will stand for positive and 0 will stand for negative. Okay, so let's try that. Let's go back to our script, and let's say that I'm going to create a new variable in the PIMA Indians diabetes data set, $binary. I'm going to call my binary field simply binary. Okay, reverse arrow. What I am going to do is I'm going to use the trick, our trick, as.numeric, and then PIMA Indian diabetes data set, $diabetes. Okay, so I am converting my factor to numeric to have the numbers 21212121, and I'm subtracting 1. I'm subtracting 1 to convert it to 101010. Okay, let's run this line of code and pop up the data set. Scrolling all the way to the right. And for the positive, this one is a factor. For the positive, I'm seeing a 1. For the negative, I'm seeing a 0. Okay, positive 1, negative 0, and so on and so forth. I can go all the way down, and for all of the positive diabetes, I'll see a 1, and for the negative diabetes, I'll see a 0. Okay, so now we're ready to go. All of our features are numeric, and our labels are 1, 0, numeric as well, binary. Okay. Since all my data is numeric, what I can do now is split my data into testing and training. If you don't remember what that means, please go and see our previous episodes where we describe testing and training data sets and how to split them randomly or by stratified sampling. Okay, so what I'm going to do now is I will actually split our data. I will create a vector with our training indices. So I'm going to say train_index, reverse arrow. And I'm going to sample from 1 through 768. 768, which is the count of observations from our PIMA Indian data set. 768. Or I could say n row of PIMA Indians diabetes data set. Okay. Now the sample size, the size should be equals to, I'm going to assume 80%. So 0 times 0.8, 0.8 times n row of PIMA Indians data set, PIMA Indians diabetes data set. Okay. So this is how my training index looks like. I'm going to take 80% of my PIMA Indians diabetes data set and get a sample, a random sample of it for my training index. Okay, let's run this. Control, Enter, Command, Return. So I have it. If I go to my environment, I will see my train_index, an integer of length 614 observations with random indices for my data set. Okay. So now what I can do is I can build my training data set. So I'm going to say train_data, reverse arrow, and from the PIMA Indians diabetes data frame, I am going to want to do the squared brackets, comma, and in the row indexes, I want to include all of the train_indexes. Train_index, and I want all the variables, all the columns, so I'm leaving this empty. Okay. Putting it in a new row, just for clarity. Okay, good. So if I run this, I will get a beautiful training data set with 614 observations and 10 variables. Okay. So it's 80% of my data. On the other side, I'm going to build a testing data frame. So test_data, reverse arrow, PIMA Indians diabetes data set, squared brackets, comma. In the row index, I'm going to say minus train_index, minus train index. I want to exclude all the indexes that went to my train data, exclude them. Right? So if I run this line of code, Command, Return, Control, Enter, I am going to get my test data with 154 observations and 10 variables. Okay? So as you have noticed, if we add these two together by observations, we'll get the full Pima Indians diabetes data set. But for now, I have my training data, 80% of the initial data frame, and my testing data, 20% of the initial data frame, all variables included. Okay, good. We are ready to build our logistic regression. We will use the GLM function. So let's do it. GLM in our script, GLM parentheses. And here I have to start this function with my formula, with the formula for our model. I'm starting with the dependent variable, with our binary variable. So I'm going to say binary. That's how we called it, right? We created a new variable called binary. Binary, and then the squiggle. The squiggle is just below the escape button, but I have to click shift and then the squiggle. The squiggle will indicate causation. So we are trying to predict binary with something. With what? We're trying to predict binary with, let's say, age plus mass plus, let's see, what else do we have here? How about pregnant plus triceps, okay, plus triceps. Okay, now data will be equal to train underscore data, okay? I'm using my training data set, 80% of the initial data set, comma, and last but not least, the family option. Family has to be binomial. This is how I tell R that my model is a logistic regression. Family equals binomial. So when I run this, I get a beautiful model down here. And let's see. The output gives me my formula, my GLM function. It gives me also all of my coefficients. The intercept, that I don't really interpret in logistic regression. It's very hard to do that. The age, the mass, pregnant, and triceps. So coefficients for all of my independent variables, my features, okay? And just to point out here, something very important, I'm gonna get something called deviance residual, the residual deviance. And I'm looking at the bottom of my console. Residual deviance, 696.4 and AIC, 706.4. AIC stands for Akaike Information Criterion. Japanese statistician that calculated this criterion to compare different models. So with these two parameters, we can then compare different models. But about that in the next episode. But now, what I am missing from this output is, for example, the statistical significance of all of my coefficients for all of these features, right? I don't see any p-values. Maybe these coefficients are statistically insignificant. To get that, I am going to have to save this model in an object. So just going back to my script, to line 14, just before the GLM, I am going to give it a name, my underscore logit, reverse arrow, and then the GLM function. Okay, so I will save my logistic regression in a object called my underscore logit, command return control enter on that line of code. And now, of course, the model in my environment, I'm looking up here, is a list of 30 elements, and it's just insane in there. If you actually want to investigate what's inside, it looks ugly, all right? But now what I can do to make it look pretty and get more insight, business insight, is I can run a summary function on my underscore logit. So let's do that. I'm going to use the summary function in my script, parentheses, and use my underscore logit to get some information regarding the model. And here it is. Okay, so once again, let's go to my console and take a look at the output of this summary function. I'm getting the same GLM formula with my model listed out, and I am getting something called deviance residuals. This explains how good the model is. So we can compare the median deviance residuals between different models and then select the one with the best deviance residuals, okay? Now, what I also want to do is take a look at the coefficients coefficients. I have my estimates, which are my betas from the model. I have age, which is 0.027702, the mass, which is 0.105416, etc., etc. And I have my standard errors, z-value, and p-values, So if the p-value is less than 0.05, in our case, then we will say that it's statistically significant. If it's above 0.05, we say it's statistically insignificant, which means that it's no different from zero. Okay, so I'm looking for statistically significant variables. In our case, statistically significant are age, right, below 0.05, mass, below 0.05, pregnant, below 0.05. Also, the stars help me understand the significance. If you forget about the p-value rule, follow the stars, and depending on how many stars we have, that's how significant this variable is going to be. The only insignificant variable is my triceps, so I will try to exclude triceps from my model. Let's do that. I'm going to exclude triceps from my model. So going back to my script, to line number 14, I'm going to exclude triceps and leave age, mass, and pregnant. I'm going to rerun this model, command, return, control, enter, and the summary for this. Okay, so now if I go to my console, I will see that all of my variables, all of my independent variables, aka features, are statistically significant. All the p-values are below 0.05, and the stars indicate the significance of the variable, of the coefficient, estimated coefficient. Okay. How do we interpret these coefficients, right? Well, we use the exp of this coefficient. So for age, I'm going to say exp, open parentheses, 0.028052. Okay, now -1 to make my life easier, right? Command return, and the answer is 2.8%. So with every additional year that I'm older, when I get older by 1 year, the odds of my business success, which in our case is getting diabetes being positive, a positive test for diabetes, not too good, but whatever. The odds of our business success increase by 2.8%. The odds of business success, in our case, the positive test for diabetes, increased by 2.8%. Okay. Let's take a look at the mass. I'm going to say exp of 0.102573 -1. Command return, control enter, and the result is 0.1. So it's a 10%, almost 11%. So with every additional unit of mass, the odds of our business success will increase by 10.8%. The odds of success will increase by 10.8%. Okay. And then last but not least, the pregnant variable. Again, exp, the exponent of 0.089370 -1. Command return, control enter. 9%, a little bit above 9%. So what this means is that for every additional unit of pregnant, which I believe is the month of pregnancy, okay, month of pregnancy. So with every additional unit of pregnant, the odds of our business success increase by 9%. 9%. Beautiful. We know how to analyze our model. We know how to drive business insight and some findings from the model coefficients. We know how to interpret the summary, how to interpret the EXP of our coefficient in terms of the odds ratio. But now, how can we actually create business value? Value for the business with this model? Well, I can use this model to classify new Pima Indians, new customers walking through that door into our hospital, okay? And to do so, I will use the predict function. Let's go back to our script. And I'm going to use the predict function and parentheses. In these parentheses, I'm going to call my underscore logit, which is our logistic regression model, saved in the environment. And I'm going to use this logistic regression model on the test underscore data. This test data was never seen before by the model. We used the training data. The test data represents new people, new customer, never seen before. Okay, test underscore data. And then what I need here is to specify the type. Type equals response. And by using type equals response, I'm telling R to predict the probability of business success, which in our case means a positive diabetes test result, for all of the test subjects, all of the new customers, right? Okay, so probability from 0 to 1. Any probability greater than 50%, than 0.5, will indicate a business success label. Anything below 0.5 or 50% will indicate a business failure label as 0. Okay, so let's run this line of code. And let's take a look at the outputs in our console. Okay, in our console. The first test observation, the first test object with an index of 12 has a prediction of 0.6, 60% probability of business success, which means that it was labeled as 1, as business success. The second one, this one is tricky, index number 13, 49% of chances of business success, 49% probability of business success, which means that it's below 50%. I will label it as 0, as a business failure, because it's closer to the 0, right? But this one is tricky. It's so close to 50%. It's so close to 0.5 that I'm having really hard time believing in the 0 label. Okay, this one is right in between. Okay, let's take a look at observation 23. It has a 63% probability of a business success. So I will label this as 1, as positive. Now let's take a look at the last one, the one with index 43. And of course, you'll have different test subjects because your script will split your data differently. You might have different results here because your test objects, your test observations might be different. But I'm taking a look at this one here. So for index 43, my probability of success is 26.7%, which means it's closer to the business failure, to a 0, to the negative test result, right? The probability here is so low that I can confidently, with a huge dose of confidence, label this as a business failure, as 0.
You might have noticed that we are in a forest, and there is a reason for that. A forest is another machine learning model, okay? But more about that in our next episode and our next session. By the way, this is the Purisima Creek Forest, very close to Half Moon Bay at the Pacific Coast, West Coast in USA. Beautiful place for hiking, biking, spending time with your family. So come and visit.